Even with all our modern theories, the nature of gravity is still such a mystery to us. What is it? Where does it come from? Unfortunately, if you ask YouTube these questions, you're going to get some wrong answers. Some very wrong answers. Namely, you're likely to come across an explanation which purports that time dilation is the cause of gravity. Indeed, almost as mysterious as the origins of gravity are the origins of this popular yet confoundingly incorrect explanation. Where did it come from? What does it mean exactly? And what can we learn about the actual nature of gravity from it? This is Dialect with the true cause of gravity. Understanding general relativity is no easy feat. The central concept it relies upon, curvature, though mathematically well-defined, often eludes clear interpretation. Indeed, nowhere is this more apparent than in a recent spate of YouTube videos, all of which erroneously attempt to attribute gravity and curvature to time dilation.
Gravity does not warp the flow of time, it's the other way around. The warping of time causes gravity. That's what I'm going to show you right now.
The type of time dilation involved in that building experiment is called gravitational time dilation. Not because it comes from gravity, but because it causes gravity. I know.
On the surface, these videos and their explanations seem pretty cool and convincing. Each video starts out by noting that the further out you are from a gravitational mass, the faster clocks tick.
This causes the clocks near the Earth to run slower than clocks far away.
For example, time passes more slowly the closer you are to the Earth.
When charted out on a space-time diagram, this leads to a time gradient or temporal flow about a gravitational mass.
We have this sense of time flowing in a gradient. Faster streams distant from the Earth, slower streams near it.
And just like an object caught in a river with an eddying current, any smaller mass near the central one will be forced to rotate towards it, meaning rotated out of the time direction and into the spatial direction.
Over time, it points more and more toward the Earth.
Parts of the object will want to move through time at different rates. Hence, we have the appearance of a gravitational attraction.
If you were like us, your first reaction upon hearing this explanation was probably,
Whoa, dude.
yeah, whoa, that's freaking awesome, mind-blowing. Mass and energy cause time dilation gradients, and time dilation gradients rotate the paths of objects through space-time so that they come together. That's gravity. It all seems to make so much sense. But then, on further reflection, you might have started scratching your head. Wait, is the whole current gradient thing supposed to imply that there's like an intertemporal force binding an object to its future self, and which causes it to hold together after being rotated by another sort of strange, temporally directed torque? Like, what? Suddenly, you're lost in a very murky analogy. Even Matt from PBS Spacetime admitted he was still a little confused by this interpretation.
Well, speak for yourself. I'm still quite confused. This raises thorny questions.
Well, the reason for your confusion is simple. You're confused because the explanation is wrong. 100% unequivocally completely wrong. It's astounding that not one of these videos did their homework properly, because this entire interpretation, with its multitude of YouTuber proponents and its millions of beguiled viewers, comes undone with just a few simple considerations. Now, before we begin, we need to make some important distinctions. There are 3 different phenomena under consideration here: curvature, gravity, and gravitational attraction. Now, in Newtonian physics, gravitational attraction and gravity are one and the same thing. Masses are the source of a gravitational force, gravity, which thereby causes gravitational attraction. In general relativity, however, gravitational attraction is only an apparent phenomenon. It's fake. Meanwhile, gravity and curvature become one and the same thing. Where you have curvature, you have gravity. Where you have no curvature, you have no gravity. And lastly, where you have accelerating frames of reference, you have apparent gravitational attraction. So the first important takeaway here is that this apparent gravitational attraction is not gravity. That is, it is not spacetime curvature. Now, half of these videos don't understand whether they're trying to explain the cause of apparent gravitational attraction or the cause of actual gravity, i.e., spacetime curvature. Being separate phenomena, these two concepts actually require separate explanations, and we'll get to that later. But at the moment, this doesn't matter, because none of these videos succeed at explaining either phenomenon. They're all wrong on all counts. To see why, let us first consider a uniform gravitational field. Now, the argument in all these videos hinges on the fact that time dilation gradients, that is, clocks ticking at different rates at different places, will cause different masses and objects to come together.
Remember, time passes at different rates in different places. The heights of the clocks don't have to be that different though. Any difference will do. So imagine we attach 2 clocks to a squirrel, one on his head and one on his feet. They should tick at different rates too. The squirrel's head moves faster through time than his feet. This gradually turns his motion arrow. The squirrel falls to the ground simply because time dilation exists.
Now, a uniform gravitational field has a time dilation gradient. And certainly, at a place like near the surface of the Earth, where the gravitational field is essentially uniform, objects seem to be drawn together. So, all good, right? Nope. Why? Because the equivalence principle. The equivalence principle tells us that a uniform gravitational field is actually just an accelerating frame of reference. Imagine being on a rocket ship in outer space, undergoing constant acceleration. According to your perspective, there arises a uniform gravitational field filling all of space, causing clocks that are further and further out from you to tick faster and faster. Now, imagine coming to rest. Suddenly, all those clocks resume ticking at the same rates, and the time dilation gradient abruptly vanishes. If we accept the explanation purported by these videos, that time dilation gradients are the cause of gravity, this would mean every time you accelerated, you would be inducing gravity. That is, inducing space-time curvature. Not only in your immediate vicinity, but across the entirety of the universe. Curvature which would vanish as soon as you stopped accelerating. This is patently absurd, of course. Space-time curvature is not an observer-dependent phenomenon. It is something that, according to the theory of general relativity, all observers will agree upon, no matter what their frame of reference. And a uniform gravitational field, in fact, has zero curvature, because there is no gravity there. It's just an accelerated frame of reference. All right, let's return to the surface of the Earth. You're probably most accustomed to experiencing gravity here in your day-to-day life. It might shock you to learn then that at the surface of the Earth, there is no gravity. None whatsoever. The reason the apple falls to the Earth isn't due to the fact that clocks at the top of the apple are, from the perspective of an individual on the ground, ticking slightly faster than clocks at the bottom of the apple. Rather, it's due to the fact that you, the observer, are accelerating upwards through space at 9.8 meters per second squared. You and the ground beneath you are literally rushing up to meet the apple, as well as towards anything else that might happen to be falling at that moment. And that is the true cause of apparent gravitational attraction. The fact that you're accelerating when you believed yourself to be stationary. Time dilation is a relative phenomenon. Gravity, as in real space-time curvature gravity, is not. The fact that clocks tick faster at higher elevations is certainly true for observers who are observing those clocks while on the ground accelerating. However, if we transform into the inertial frame of the free-falling apple, the clocks at both its top and bottom will be ticking at exactly the same rate. Thus, the fact that all these videos attempt to assert that apparent observer-dependent time dilation gradients are responsible for real observer-independent gravity is absurd and doesn't make any sense. But what makes even less sense is that, in promoting this idea, all these YouTubers somehow managed to completely forget the basic fundamentals of general relativity. Yet, they're obviously not unintelligent individuals, so that leaves a whole new mystery. Where did this explanation come from? And why was it so convincing? The answer lies in a pretty simple fact. Everyone who pushed for this explanation mistook a space-time diagram for actual space-time. To see what we mean, let's turn to Idealist's video. Despite being a smaller channel, the level of explanatory power and clarity evident in Idealist's video far exceeded that of all the other channels. And we thank him for that, because without his video, we wouldn't have been able to get to the bottom of this, enthralling mystery.
The white lines show that for an equal amount of bottom floor hours, higher up clocks travel further in time. An intuitive way to estimate the geodesic between two lines in this curved spacetime is to start at a point on a time grid line, then use a circle to find the shortest path to the next time grid line. Let's think about an apple hanging from a tree in this new context. It will follow its geodesic through spacetime, its shortest path, which just so happens to coincide with the apple falling towards the center of the Earth in space.
As you can see, Idealist notes that at higher elevations, where clocks tick faster, the world line of an object on the spacetime diagram will be forced to curve if that object wants to take the shortest path between coordinate grids. But Idealist's mistake here, like all the others, is that he interprets the spacetime diagram as being actual spacetime. That is, he thinks these objects are actually curving through time and space, simply because they're curving on the diagram. He conflates curved lines on a spacetime diagram with spacetime curvature.
This is the sense in which spacetime is curved here. Because this spacetime is curved, geodesics through it will also be curved. This spacetime is curved.
Spacetime is curved. Spacetime is curved.
Now, a spacetime diagram is a tool. It is not actual spacetime. Like taking the curved surface of the Earth and making a flat map of it, it is a representative depiction, an aid to assist in understanding. So if we want to know where and how curvature appears, we need a mathematical test more precise than simply pointing at curved lines on a spacetime diagram and going, spacetime curvature. So here's what we'll do. Let's note first that, mathematically speaking, curvature arises wherever geodesics on a surface are either converging or diverging. Consider two great circles on this sphere, for instance. Note that, as we traverse them, the separation between these geodesics either grows or shrinks. This indicates curvature. If the surface were flat, the geodesics would remain parallel, and the separation distance between them would never change. Now, let's return to the surface of the Earth. Position a bunch of apples at different elevations and release them simultaneously with respect to the accelerated observer on the ground. Next, construct a spacetime diagram from the perspective of this accelerated observer. Since the gravitational field that the observer perceives here is uniform, all of the apples will fall at the same rate, and their trajectories will form a series of staggered parabolas. Because the paths of all the apples were inertial paths, we know that these parabolas are all geodesics on the spacetime manifold. Now, let's examine the separation between these geodesics. Notice something? Despite all these paths curving, the separation between them never changes. This means there is no spacetime curvature here, and thus no gravity. Now, if we zoomed further out and dropped our apples from higher and higher elevations, we would start to notice that the separation between geodesic world lines would begin to grow. This would indicate spacetime curvature. This is where true gravity finally makes its appearance. So when Idealist and others thought they were looking at spacetime curvature, they were in fact looking at something else. What exactly? Well, let's trace this idea back to its origins. You see, PBS Spacetime acknowledges borrowing this idea from the Silence Asylum, who probably borrowed it from Eugene Kurturayansky, who probably got it from this dude, who in turn likely got it from this 2013 video. After that, the trail goes cold, but this early video is enough to show us what's really going on here. Ready? Watch. As you can see, it's just a simple coordinate transformation. Specifically, it's a coordinate transformation mapping a parabola to a straight line. And this curving on the diagram, which results from the rotation of the coordinate system of the accelerated observer, and not from the rotation of actual world lines of objects through space or time. Everyone has confused for either actual space-time curvature or apparent gravitational attraction. So basically, all of YouTube got tricked by a coordinate transformation, forgetting to remember that, in relativity, coordinates don't always mean what you think they do. Okay, now back to gravity. If all these videos are wrong, then what is the true cause of gravity? Well, that answer is the same one Einstein and essentially Newton gave: mass and energy density. That's the only factor which determines the amount of space-time curvature or gravity in a given region. Interestingly enough, this means time dilation has nothing to do with curvature. In fact, you can build a theory of curved space-time without time dilation, using only the classical concepts of time and space from Newtonian mechanics. It's called Newton-Cartan physics, and what it demonstrates is that general relativity actually has a lot less to do with relativity than its name might lead you to believe. But that's a topic for another day. Okay, but the question that you've been really asking yourself since this video started is, what causes two objects seemingly at rest with respect to one another to become drawn together? Well, to explain that, you simply need to invoke gravity, the internal pressures within a mass, and apparent gravitational attraction. You see, no single mass is truly ever at rest with respect to itself. This portion of the surface of a spherical mass, for instance, is accelerating out from the opposite portion of that mass by a certain amount, while that opposite portion is also accelerating away, but in the opposite direction. In fact, every portion of a given mass is accelerating away in a radially outwards fashion from the rest of the mass. Now, such masses don't blow apart into 100 pieces, because real gravity, space-time curvature, steps in here to ensure the space-time manifold is warped in just the right way as to compensate for all that outward acceleration, and thus produce a stable configuration. Hence, we have the appearance of a universal attraction affecting all bodies, because every single mass in the universe is literally accelerating towards every other single mass. Granted, this is a very abbreviated explanation, but it's a much closer step towards understanding the truest cause of the attraction between bodies. Lastly, we'll note that there is a way to interpret an accelerating observer's rotating planes of simultaneity as a sort of one-dimensional temporal curvature. However, this curvature would not be space-time curvature. Rather, it would be a coordinative curvature which we could transform away, unlike real curvature. Nor would it explain apparent gravitational attraction, since the attraction between bodies in this case is, again, obviously explained by the fact that objects are just accelerating towards one another. Well, this has been a lot. So, to conclude for today, We will say that general relativity is obviously confusing, and we can forgive these YouTubers for getting it wrong. But the question remains, will Science Asylum, PBS Spacetime, or any of these other big league bad boys acknowledge their mistake and help to rectify the misconceptions they've propagated unto their millions of viewers? Well, we appeal to you, our viewers, to take up this mantle and help spread the word, because, frankly, we're exhausted after sorting through this mess, and we need a vacation. But don't worry, we'll be back. This has been Dialect. Thanks for watching.